That ends up being handy. Okay, so I should be recording my screen now, and hopefully it doesn't kill my computer to do this. So the simplest kind of differential equation to solve is something like this. So I'm going to write y prime here, just because that's a little bit easier. So let's see. Let's say I have something like f of x. Okay? So what this is asking me for, I would note the prime here. What I'm looking for is a function y equals something or another, such that when I take the derivative here, it's kind of implicitly understood here that y is something that depends on x. And when I take the derivative with respect to x, f pops out. Well, that's something that we already know how to do, right? That's called taking an antiderivative, right? Or integrating something indefinitely. So this is just an indefinite integral. So for instance, if I have y prime equals, I don't know, 2x, then so there's kind of maybe a little bit more visual way of saying that this is just taking a derivative. So let me put a display style in here. Y prime is just dy over dx, right? Those are the same. Those are two different symbols that mean the same thing. So I'm going to say the differential dy is going to be equal to 2x dx. And if you want to make me very sad, you can say I multiplied dx across, but no, I'm saying this, which is something else, is the derivative times some increment dx, okay? It actually is helpful to think of this in terms of differentials, though. A little bit of y, so a slight increment in y is equal to 2x times a slight increment in x. We'll come back to that when we start, when I talk about Euler's method. So then what I can do with this equation is I can integrate both sides. And since these are equal things, when I take the integral of them, they should have the same indefinite integral, right? So integral of dy, I need to put an integral sign in there or it's going to look weird, equals integral of 2x dx. So, okay, what's happening here? So I'm integrating this left side with respect to y. I'm integrating this right side with respect to x. And so here's what I'm going to get. On the left side, I have integral of 1, basically. And that's going to be y plus a constant. And then on the left side, I'm going to have x squared plus a different constant. So I have a constant of integration on each side here. But one thing I can do to make this a little bit simpler is I can just combine these constants. And a constant minus a constant is another constant. So I can just say y equals x squared plus c. Okay. Did everybody follow that? Are there any questions over the bit I just did? Awesome. Great. You know, you can, if you know, this isn't, you know, I'm not the only one that has to talk. This is for y'all. So like, if you need to unmute yourself and ask me something, you can unmute yourself, you know, or just say hi. We're just chilling. I'm not really your TA. I'm just somebody who's excited to talk about math with you. I think of it like that. Okay. It's my pleasure. So let's see. So there's a name for what I just did here. It's called, what I have just done is I found what's called the general solution to the differential equation y prime equals 2x. That is all a general solution is. What makes it general is that it's kind of like, I'm sure there was some consternation when you first learned about integrals and you learned that you had to write plus c at the end of it, because any constant, it does not matter what this constant c is, this is still going to solve this differential equation if no other constraints are given, right? So that's what makes it general. It has an undetermined constant in there. Well, let's suppose I want to find, there's something you can do with something called slope fields. And if you have, that'll make more sense after I'm done talking about this. So let me finish this first. So let's say I decree, let's say I want this equation to satisfy, I don't know, let me make up a number, y equals 10 when x equals 4. Well, now there's infinitely many functions in this general solution here because there's infinitely many choices of constant, but only one of these should satisfy this additional constraint that I've thrown in, right? So this y equals 10 business here, this is what's called an initial condition. And it determines the value of the undetermined constants. So if you remember something about solving systems of equations, I need, if I have two undetermined coefficients, I'm going to need two initial conditions. So let me say actually n undetermined constants, I need usually n, most of the time these are going to be linear equations, and then you have a system of linear equations. So to determine a unique solution that satisfies them all, this is called a particular solution. Okay, so how do I find a particular solution in this example? Well, all I have to do is plug in. So y equals 10, x equals 4. So I know 10 is 4 squared plus c. And if I solve for c, that gives me -6, I believe. So I say the particular solution is y equals x squared minus 6. So that's hopefully, does that demystify all the lingo in that WebAssign question up there? This is all you're really doing. Anybody, any questions here so far? Next thing I'm going to do is this WebAssign example, I think. So let me move myself out of the way so I can see it. All righty. So here's an example. So let's see what this says. Verify that the general solution, and I'm going to put what things are next to the term for them. So I'm going to say 5x squared plus 6y squared equals c satisfies the differential equation 5x plus 6y y prime equals 0. Then find the particular solution that satisfies the initial condition y equals 2 when x equals 5. So that looks like what that WebAssign question is saying. So, okay. First thing I really ought to do is this verification business. But basically all that would be is me doing implicit differentiation and then showing that that's what pops out. So let me do that and then let me integrate it. So if I do implicit on this equation here, I get, let's see, implicit derivative of 5x squared is going to be 10x. Implicit derivative of 6y squared is going to be 12y chain rule times dy dx, which is y prime, equals, on the other side now, implicit derivative of a constant is 0. And so now if I cancel the 2, we get 5x plus 6y prime equals 0, which was what we wanted. Why do I put dy dx for chain rule? Okay, so you're saying when I do implicit, why does a y prime show up where it does? Yeah, okay. So to put this in context, the question was, how do I get from 6y squared to 12y y prime? So remember what chain rule is. So so that's when I have to take the derivative of what might be called a nested function. So I've got like f of g of x, something like that. Well, think about what y squared is here. This entire problem is kind of taking place under the implicit assumption that y is a function of x. So it's y and its derivatives that show up, not x and its derivatives. So y is kind of my dependent variable here. So back to 6y squared. I'm taking the x derivative of 6y squared, right? So y depends on x, but I'm squaring y, right? So when I do the x derivative of that, remember how chain rule goes. I differentiate the outside like there's no problem. So y squared would become 2y. But then chain rule means I have to multiply by the derivative of what's inside the square, right? So in this case, that's y. And the derivative of y is just y prime or dy dx. Does that answer your... So yeah, that's so then the follow-up was you wouldn't do that if it was y instead of y squared. That's not how I would say it, but you've got the right idea. So let's say I'm taking the x derivative of y, which depends on x. If you want to be picky, you could say the derivative of y without worrying about anything is 1. But then I have to multiply by the y prime. Same as if I had a y squared there. But ultimately, you can think of it as just take the derivative of y, you get y prime. So the squared is really what makes the chain rule have to kick in. If you're right in that sense. Okay, is that good? Gosh, I'm never going to get over being called a queen. It's the best. I would change my last name to Valor, but I'd get sued. Okay. This is my one look, and I'm just going to go with it for the rest of my life. I'm going to be bald the rest of my life. I'm going to have black lips the rest of my life, big glasses, hoop earrings, septum piercing, and that's just going to be the way I live until the day I die, and it's going to be fabulous. I am the best gender abomination that... Oh my gosh, I love you people so much. You make me so happy. Quarantine. Oh gosh. I love it. That's probably not something I should be saying out loud, but I don't want to appropriate anything or use AAVE where I shouldn't be. So, all right. Let's move on to talking about what Euler's method is. So the first thing that they tell you about differential equations is most of them you just flat cannot solve. So this is an extension of how there are some some functions that you can't integrate in elementary functions. So I know you got that talk because I'm pretty sure I gave it to you. So like something like sine of x squared, I cannot integrate and get a function that I am familiar with. That function does have an antiderivative because it's continuous, but I can't describe it any more nicely than basically the antiderivative of sine of x squared. So, okay. Oh, shoot. I never did the initial condition bit. Whoops. Okay. So I'll get back to that business in a second. Let me finish this problem first. Shoot, where was I? All right. So now to find the initial condition, or sorry, to find the particular solution, we plug in the initial condition. And this won't take but a second. 5, let's see, x is 5 squared plus 6 times y is 2 squared equals c. And so all I have to do is figure out what that is, and that looks like it's going to be 125 plus 24 is 149. So my particular solution is 5x squared plus 6y squared equals 149. So what's the upshot of all of this? This is a lot of big fancy math words for something you already know how to do. This part is, anyway. Euler's method is kind of new. But why does WebAssign make this so much more complicated? I don't know. I hate to say this. This one isn't really... Okay, this one is not on WebAssign. This is on mathematicians making things more complicated. I believe it, yeah. If you saw all this terminology and you didn't like have the perspective on it to know what it really meant, then yeah, I could see you kind of getting completely lost, and because it's a lot and it comes at you so quickly that what you actually have to do to solve it is not something that you should be freaking out over, because it's very simple. All right, so let's talk about Euler's method. So almost all differential equations, you cannot write down a function that gives you the solution. This is like how you can't write down a function whose derivative is sine of x squared that's any better than, and when I say better, I mean fewer integral signs, than the integral of sine of x squared dx. So I know you've already gotten this talk, but I'm going to give it to you again. When I say you can't do it, I don't mean you can't do it because you're only in Calc 1. I mean you can't do it. In fact, it's been proven that you can't write down integral of sine x squared in what are called elementary functions. So the things you learn how to take derivatives of in Calc 1. It just can't be done. It doesn't exist. While we're here, though, I want to show you a fun math thing because I can. I know I'm getting distracted, but that was called Euler's method. Let me show you something else named after Euler. So check this out. Doesn't that look cool? So this was a graph that was drawn. It looks like an actual graph of, it's not a function, it's kind of plotted parametrically. But yeah, it's great, isn't it? So I forget which way it goes. It doesn't matter super much. I think it's the x coordinate here. So, okay, let's talk about what this is. This is a parametrically plotted function. So what that means is, instead of having y depend on x, so that's where vertical line test comes in. Vertical line test doesn't let us do everything we want to. This is a function for which x and y are both plotted with respect to a time variable. So we usually call that t. So I have an x of t and I have a y of t. So you can think of this as, this is really two functions. And one of those is the, tells me the x coordinate, and the other one tells me the y coordinate. If you'd like to guess what these two functions are that make this graph up, one is the integral of sine of x squared. One is the integral of sine of x squared. The other one is the integral of sine of cosine, the other is the integral of cosine x squared. And they converge on this point where there's a plus here as t goes to infinity. You can prove that this point has the same x and y coordinates for starters, and that coordinate is the square root of pi over 2. So you can actually do this. So you can't write down an antiderivative of sine x squared, but you can actually compute the integral from 0 to infinity of sine x squared, and that's square root pi over 2. And if that doesn't blow your mind, I don't know what's going to blow your mind. That's so cool. Also, it's pretty. Not as pretty as my face, but that's okay. Okay. Yeah, this is so cool, though. I love it. Straight facts from the cat and printer. I love you all so much. You know what the most terrifying thing is? I've had long-standing self-esteem issues for a while now, and let me find. Here we go. And this look just completely did away with all of that, because I look in the mirror and now I'm like, oh my God, I'm so powerful, and it's insane. It's my pleasure to help. Thank you so much. It is, I love you so much. Also, just so we know, this is going to go on for as long as you need it to. I will be up all night for you guys if you need me to, you guys and you gals and you non-binary pals and others. So there's a hard cap on the meeting time, so it's more than 40. It can't go longer than 40 minutes. You know that already. But we're just going to keep doing what we did for. Your queen has at some time or other been like most genders, so it would be hard for me not to be inclusive. I just try to do my best. Okay, where was I? So for most differential equations, the best we can do is solve numerically. And there are a few ways to do this. The simplest is called Euler's method. And so here's what Euler's method is. How should I couch this? So okay. So let's say we have a differential equation. Let me just pick something easy like y equals x squared, or sorry, y prime equals x squared. There we go. And an initial condition like, I don't know, something nice. When x is 3, y is 5. I don't know. Maybe make it y equals 9, so my numbers aren't so bad here. When x equals 3. Okay. So what I've got here is a differential equation and an initial condition. So here's how I want you to think about this now. Once my page loads here. Okay. So this is a picture of what's called a slope field. So, okay, why is it called that, and what are these little lines on it? Well, those are kind of the same question. So remember, y prime dy dx, that's a slope, right? We think of it as a slope of a tangent line. But in reality, you know, that's kind of, I don't know if in reality is what I should have said. But when you see dy dx, you should think that's a slope of something, right? So if we were to integrate that function that's on the other side of this, then that function would have some tangent lines at different points, and dy dx would tell us what those tangent line slopes are. So here's what this is. These slopes are they indicate, I should say, they indicate the values of dy dx at different coordinates here. So this looks like it's about -1 here, or maybe -2. It doesn't look like these are super plotted completely the same. Oh, I see, the axes aren't the same. Okay, that makes a little bit more sense. So, okay, so like at 0, 0, if I plug 0 for x in, I'm going to get -2. If I plug 0 for y, I'm going to get, wait a minute, that doesn't make any sense. If I plug, I don't know, 2 in for x, I'm going to get 0. So, or something very close to 0. So so the slopes around x equals 2 are all very flat. Same for -1, which is the other 0. And hopefully this makes sense. So the idea should be basically, if these are the tangent lines to the slopes of a function, sorry, if these are tangent lines to a function, which is, you should think of these as little bits of a tangent line, then I should be able to reconstruct. Oh, you will see me around, I promise. If there's classes next semester on campus, I will tell you all how to reach me. I love you, and have a good summer, and good luck on your final. Okay. So the idea is you should think of the idea is you should be able to reconstruct the function by following the tangent lines a little bit and switching over occasionally to whatever the new tangent line is at the point you are at now. So I follow this one, and then I follow this one, and 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 this one. That's a simple idea, right? That's all Euler's method is. I promise that's all it is. So let me find my thing here. Euler's method works based on an initial condition, and that's a point that we start from, and what's called a step size. And that's exactly what you would think. It's how far we move at a time. And it's going to be how far we move at a time in the x direction, and we're going to let the slope tell us how far we move in the y direction. So step size is like I take a step size, I take a step size, I take a step size, and so on and so on and so on. That's all it is. Whoop, 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 whoop. So, and usually we call the step size h, or some people might call it delta x because that's kind of what it is. I don't know. So let's just make some stuff up. Let's say h equals, let's say h equals a half. Approximate the value of the function that satisfies the differential equation and the initial condition at, let's say, x plus a few step sizes. So let's say x equals 4. So that is 2 step sizes away. This would be so much easier if I had a piece of paper to draw on, but that's okay. So let's see. I might want to make a table for this. Let me sketch that out on a notepad real quick so I know how many rows I need. All right. All right, I think I can get by with 5. So 1, 2, 3, 4, 5. And so, uh-oh, that's not what I want. So here's what I want to say. For each step, I'm going to have a line. And so I'm going to have an x value and a y value. I'm going to have a slope at this point where I am. And I'm going to have a delta y. In fact, let me write it a little bit nicer. Okay, everybody cross your fingers. Hey, that's pretty nice. All right. Let me put a horizontal line in. Do you like that? Oh my God, you do. Okay, so let's do that. Okay, so I'm going to take this one step at a time. I'm going to start at my initial point, and that's given by my initial condition. So my initial x value was 3, my initial y value was 9. My slope at x equals 3, y equals 9 is going to be my x value squared. What do you want? That's Discord going off. All right. And so my dy dx at this point, so the slope of the slope field where I am would be 9. Where was that page? Here we go. So this would look like a line that has a slope of 9 around wherever I am. Where am I? Okay. And then, so remember what I'm doing. I'm following the tangent lines, right? So the little slope pieces are pieces of tangent lines. And so I already know my x step size, that's how much I started with. That's one of the pieces of information I started with, right? And then to get the y step, I take the slope and I multiply it by the x step. So that's 4.5, it looks like. And then to get the y value, I just add the change in y to my old y value. So this is going to be 9 plus 4.5 is 13.5. That's all. So that is one step. Is everybody still with me? Are we all clear how I did this line here? Great. Great. That's all Euler's method is. I'm just going to keep doing this. Okay. So I've taken a step of 1/2 in the x direction. And since my slope was 9, that corresponded with a step in the y direction of 9/2, right? So that's an interesting thought. I'll save that for later. So my new x value is going to be 3 plus my step size. And my new y value is going to be, my y value now is going to be what I just computed. So that's the 13.5. My new slope is going to be 3.5 squared, which that's 12.25. This might get slightly bad. Okay, whatever, we'll worry about it later. So, all right, let's see. And then this is going to be, so to get my y step size, I take the slope and I multiply it by the x step size. That's going to be 12.25 times 1/2, which is going to be 6 1/8. These numbers kind of get bad pretty quick, but that's okay. So that's going to be, so my new y value is going to be the 13.5 plus 6.1 plus 6 1/8. Blah. That's going to be 19 5/8. So there's my next step. I'm going to do one more, and that's going to give me my value at 4 now. Because, so this is the next step I have, or actually, you know what, that is my last value, because now look at what I have. I maybe should have made another column here. But my new point that I've moved to is 4 19 5/8. And I don't really care about the rest of this now because I've got my answer here. My approximate y value for x equals 4 is this number. Now, I picked something that I could actually integrate so that I could check this. And so I'm going to integrate that real fast, and I'll get y equals 1/3 x cubed plus a constant. So this is my general solution. To get my particular solution, I'm going to plug in the values I had. So let's see. So I've got 9 equals 3 cubed over 3 plus c. And I'm just going to tell you that 3 cubed over 3 is 3 squared, which is 9. So c is 0. So my particular solution is just y equals x cubed plus 3. So if I plug 4 in for x, what do I get? That's going to be 64 over 3. And that is 21.3 repeating. So Euler's method isn't the best, but it wasn't that far off. It's about 1.5 off and some change. The reason that it's kind of off like this is that the actual equation, so like the actual y equals x cubed plus 3, increases more quickly than any assortment of straight lines, which is what Euler's method uses, has. So a quadratic will eventually increase faster than any series of straight lines, and that's just the way it is, let alone a cubic, which is actually what y is. So we underestimate that. And the reason we underestimate it is it has to do with the fact that the graph is concave up. So we approximated something that's concave up, so it has a positive second derivative, by something that is flat, so it has a 0 second derivative. So we underestimated because the rate at which was increasing, and we couldn't account for all of that. If we used, so that was a lot of blather. Here's the important thing. If we used a smaller step size, like maybe 0.1, then our result would be more accurate. So that makes sense, right? If we approximate it based on more information, so our approximation was based on the 3-point and the 3.5 point. If we approximated based on the 3-point, the 3.1, 3.2, 3.3, and so on, then we would have a better approximation because there's more data there. So that's all Euler's method is. I hope that makes sense. That took a long time to explain. Anybody, any questions? Are we all still here? Can we talk about optimization? Absolutely. Is there one you'd like me to do? Like something from WebAssign or something from a test? I can certainly pick one, but I'd have to go get the book. Just in general. Okay. What about them do you, okay, that's fine. You don't have to have an example. I just thought you might. What about them do you want to talk about? So I think I have optimization stuff back up here. If I can close this stuff out. Here we go. Let's see. Okay, I picked some bad examples for this, honestly. So, is there, doesn't have to be an example, but is there a specific question about optimization that you'd like me to answer? Like, how can I get better at solving them? What do I have to look for? Okay. So Caroline, okay. You remember getting one wrong on it. Okay, cool. So let me work through this example and then, yeah, so I'm going to work through that example, and I want you to stop me when or if I do something that you're not completely comfortable with. Is that okay? So sounds good. Okay. I will put this under my optimization section. Actually, I'll make a new section. Actually, you know what? I'll just put it here. And I'll go ahead and indent all this so it doesn't show up. You will see me around, I promise. And if not, I'll at least figure out some way that we can keep in contact because I love all of you and I want you to be witness to how, you know, all that. It'd be nice. Thank you so much for coming. Okay, so where was I? So now I can close this out. And let's see. So here's what we got here. We need to enclose a rectangular field with a fence. We have 500 feet of fencing, and a building is on one side of the field, and so won't need any fencing. Determine the dimensions of the field that will enclose the largest area. I knew a guy, he was my senior at Gatton, and he's kind of a transphobe now, so I don't talk to him anymore. But he used to do a lot of fencing, and like with the rapiers and stuff, the little short pointy swords. And it's like he had his Facebook photo for the longest time was two people in fencing gear, but they have little bits of picket fence and they're fencing with those. And I always thought that was cute. That person I stopped talking to very shortly after I came out. So, all right, let's talk about this problem. So any optimization problem has to do with, it's going to be given to you typically in the form of a word problem, right? And what you have to do before you can do any calculus is to translate it into something that looks like this. To be, so I have a function and I need to maximize or minimize it. And so the function that I'm maximizing or minimizing is typically called an objective function over what's called a feasible region. And this is usually an interval. Okay. So here's what I have to do. From this word problem, I have to say, what's my, three things. What's my function that I have to optimize? Do I have to maximize it or minimize it? And lastly, what's my feasible region? So remember, the feasible region is the values that make sense. So like I can't have a fencing region and one of the dimensions is negative. That doesn't make any sense, right? So, okay. So the first thing I would do is draw a picture, but I don't think that's going to be very comfortable here. But if you just imagine here, so I've got to maximize, in words, what do I have to maximize? It's the area of a rectangle, right? So a rectangular area, that's going to have a length and a width. So I need to find the length and the width that give me the most area, right? So let's say area is length times width. And so now I have to say, what are the constraints that I have to subject this to? So what are my restrictions? In this problem, the restriction is that the amount of fence I have is finite, right? I only have 500 feet of it. And that's lateral feet, not square feet or anything like that. So 500. The restriction is on the perimeter of this thing, right? Minus maybe one side. But it has to do with the perimeter of this thing. So the restraint here is, so the three sides of this fence cannot in totality be more than 500 feet. So if you think of how a rectangle is set up, depending on how you look at it and what side is where, then my three sides are going to be 2 widths and a length, or 2 lengths and a width. I'm gonna choose that one. So now I probably want to use all of my fence that I have available. So I have 500, I want this perimeter to be equal to 500 feet, right? Because obviously if I had some fence left over, I could probably make my area bigger. Are we good so far? Awesome. And now I have to ask what values for the area what values for the length and the width make any sense, right? And so I think it's pretty sensible that I can't have a negative width, and a 0 width isn't going to be very good either. So my feasible region, we'll say, is length is positive and width is positive. Okay. So I've got all that. Oh, one more thing. And we have to maximize A, right? Okay. So let's see. My next step is I want to take the derivative of this thing, right? So I can maximize it. That's how you learn to do this in calculus. So we have to do a little bit of work beforehand before we can do that, right? Because the length depends on the width and vice versa, right? So if I know one, I know the other. So maybe if I wanted to put this into more words, we have to choose an independent there we go, variable. I'm just imagining Nicolas Cage being somewhat intoxicated as he's filming National Treasure, and he's trying to remember his lines, and he just ends up going like, "We gotta find the Declaration Independence." I stole that from a Polygon video, but it's funny. Okay, choose an independent variable. It doesn't really matter which one we pick for this one. Arbitrarily, it's getting late. We want to arbitrarily pick an independent variable. So in this case, it doesn't matter which one we pick. Sometimes it'll be easier because you want to do this thinking ahead a little bit, because you're going to have to solve for everything in terms of the independent variable, right? So I want to choose one for which that's easiest, but for this one, that really doesn't affect it too much. So I'll choose the width, just arbitrarily. So now I have to solve for all the other variables except the one to be optimized in terms of the independent variable. And so in this case, that just means getting L in terms of W. So I'm going to solve this equation here, this 2L plus W is 500 for L. And that's going to give me something in terms of W. So I think I can just say without any consternation here, that's going to be 500 minus W over 2. And now we need to plug that into our area function. And now this is only going to depend on one variable now. So I can write A of W. So this will be W times 500 minus W over 2. And interval is 0 to infinity. Let me actually write this like that. There we go. Okay, so I claim that I have done the really tricky part of this problem, which is to set it up in calculus terms. Once you have something you can take the derivative of, you should be good because that's kind of the easy part. A lot of times with these sort of word problems, getting it into calculus is the hard part. So are you good so far? Awesome, awesome. So now find the maximum. Let me make this a little bit nicer. This is going to be, uh-oh, how'd that happen? Ah, there we go. I'm just going to distribute this out real quick, and I believe that's 250W minus W squared over 2. And so to find the maximum, I have to find my critical, I have to find my critical numbers. So derivative equal, so set, I'm just going to say set A prime. And I can go ahead and take that derivative. I think that's going to be 250 minus W, right? Yeah, okay. I got spooked there because I didn't think this was going to work, but it came out okay. So, and so I set that equal to 0. That gives me W equals 250. And so I claim that there aren't any other critical numbers because there's 3 kinds of critical numbers I can have. We just did one of them. The other 2 are places where the function's non-differentiable, and that never happens because 250 minus W always exists, right? Or the endpoints. Now, I'm going to claim here that this interval doesn't really have endpoints because it's an open interval. So 0, which we would call one endpoint, doesn't belong to the feasible interval, right? It's not in there. It's where it's everything bigger than 0 is, but 0 itself is not. And then infinity, we don't really consider to be a number, so we don't, infinity is never a critical number, even if it's in the interval or an endpoint of the interval, because a critical number has to be a place a maximum can be. A function can't have a maximum at infinity. That doesn't really make sense. I mean, I guess you can think of it kind of like that, but you're going to have to use limits. So infinity is never going to be a critical number. They have to be finite, and they have to be in the interval. So maximum area is, oh, wait a second, hold on, I messed up. 0 is less than W. This isn't quite the whole interval. I can't use more than 500 feet of fence, right? So there you go. Sorry, I kind of misspoke. It was going to work out anyway, but details are kind of important when you do something like this. So, okay. So, okay, so I have to, and I guess if I wanted to be picky, I could also throw in W equals 0. That's not going to affect the problem. So those are my two critical numbers. I could do first derivative test or second derivative test to find out which one is the maximum, but I know one of these has to be the maximum. So I'm just going to plug in and see what I get. And if I let all the area be the width, then it doesn't have any length, so that's going to be 0. And then A 250, let's see. That's going to be 250 times 500 minus 250 over 2, which is, yeah, I think that's right? Yeah. And I'd like to put this in units, so that's going to be square feet. And I'll put myself a little space in there so I have something there. Okay. So the dimensions, I'll untab this too. So the dimensions that give the maximal area are width equals 250 feet, length equals half of what's left over, so 125 feet, and maximal area, wait a second, that's not, is that right? Yes, that is right, okay. Is 30, I'll say A equals 31250 square feet. Okay. There. I love you so much. Thank you for being a joy, and I'll see you, hopefully I'll see you around. I'm not going to be at WKU after next semester, so after December, but I will try to get as much of, I will try to be available as much as I can. I'll tell you how to reach me, okay? Good luck on your
Okay,
final.
thank you.
Thank you. Okay. So did that answer, does that help? So that's a blow-by-blow of how I would do an optimization problem. The only thing that I could really do to make this more complicated is to make the function like worse, or the setup worse. But yeah, I think that's something that will serve you, that's a way of thinking that will serve you better, is if you think of this as coming kind of in two phases. So number one, you have to set the problem up. Before you can do any calculus to it, you have to set it up. And then the next thing you have to do is actually solve it with calculus. Okay. I see people dropping out, so let me say before too many of you go, I know I already sent you this, but I'm going to send it to you again. This is a link to my personal website where I'm mirroring these notes that you see on my screen right now. So if I were to open it right now, here's what you'd see. So here's the thing here. I suspect you're all going to be taking Calc 2 next semester because you kind of have to because Gatton. I was a Calc 2 TA for 3 semesters. In my opinion, Calc 2 is the harder class, and I think in everyone else's opinion too. So one thing that I'm going to do to keep myself occupied over the summer is to go through my old TA notes from Calc 2 and type them all up like this. And I will make that public. And I kind of hope it gets passed down from Gatton class to Gatton class because that would be really cool. But if it helps you next semester, that's all I can ask for. So keep an eye on that link, definitely. All right. Any more questions I can help with? Where's my, here we go. Want to just hang out, honestly? I don't mind. I'm just here at 8:30 on a Saturday afternoon, just chilling, you know. It's really, it's my pleasure. This is, I love you. I love all of you so much, and I'm so glad. Being a TA it's like my favorite job ever, probably my favorite job I'm ever going to have. If I could do this for the rest of my life, I would. I love it. And I love you. Good luck on your final. I love you all. You make my heart warm. I love you all too. Thank you so much. Oh, I'll post this to YouTube. It's in the link out because I was recording this. So, all right. So you will be able to see my face forever. I think that's pretty cool. Okay, I'm going to end the meeting now unless you want to chill. All right, cool. Well, I'll stop my screen share anyway.